to find torque on the current carrying loop placed in the magnetic field. A rectangular coil EFGH is placed in a uniform magnetic field B due to two bar magnets. The length EF is L and the width FG is W. When looking from right, that is from south pole towards north pole, the current flowing in the wire is anti-clockwise, that is, the current is flowing in the direction EHGFE. Initially, the coil is placed perpendicular to the magnetic field, that is, area vector is in the direction of the magnetic field. To find the direction of area vector, curl your fingers in the direction of the current and thumb points in the direction of the area vector. We know that force on the wire of length L carrying current I placed in the magnetic field B is given by IL cross B. By using Fleming's left hand rule, we can find force on all the wires. In Fleming's left hand rule, index finger points in the direction of magnetic field, middle finger in the direction of the current, and thumb points in the direction of the force on the wire. On applying Fleming's left hand rule on the side EF, the force F1 on the wire EF is perpendicular to EF and magnetic field. It is directed vertically upward and the magnitude is equal to ILB. The force F2 on wire GH is vertically downward and is equal to ILB. The two forces F1 and F2 are equal in magnitude and opposite in direction. So, the net force due to F1 and F2 is 0. These two forces also have same line of action and hence produces 0 torque. Similarly, force F3 on wire FG and force F4 on wire HE have equal magnitude IWB and opposite direction. So, the net force due to F3 and F4 is also 0. These two forces also have same line of action and hence produce 0 torque. Now tilt the loop so that the area vector makes an angle theta with the magnetic field. Two forces F1 on wire EF and force F2 on wire GH still have equal magnitude and opposite direction, but now they don't have the same line of action. Hence they form the couple. The torque produced by them tends to rotate the coil in the anti-clockwise direction. In triangle EHI, perpendicular distance between two forces F1 and F2 is W sin theta. The torque due to the forces F1 and F2 is ILB W sin theta. The area of the loop is LW. So, torque on the loop is IAB sin theta. The magnetic moment of the loop M is defined as IA. The direction of M is the same as the direction of A. Two force F3 and on wire FG and force F4 on wire HE are still equal in magnitude, opposite in direction and have same line of action and hence produce net force equal to 0 and net torque equal to 0. The direction is found by right hand curl loop. Curl your fingers in the direction of the current and the thumb points in the direction of the area vector or magnetic moment. So we see that angle between M and B is also theta. The torque can be written as M cross B. If the coil has N turns, its magnetic moment will be NIA. This result has been derived for a rectangular coil. This result is valid for coil of any shape.